So hi, hello again. Welcome to this webinar. This is part two of predictive maintenance with Eurasian Solutions. Today I'm your speaker, your host, Jules Utmans. The rules of engagement in the webinar, I have a presentation prepared. I'll go through the presentation. There is a Q&A panel. At any time during the presentation, you can type your questions in the panel, and either during the session or and eventually also after the session, I'll start answering your questions depending on our timing. I need to keep an eye on the clock as well for everyone who is attending. So let's get started on this part two of predictive maintenance with Eurasian Solutions. So in part one, I introduced Eurasian as a company. I'll briefly do this again because there are a number of new participants in this webinar that I, also would like to get introduced to the company. So a very brief overview of Eurasian. Eurasian is a Dutch company founded in 2001. We have our offices in Delft in the Netherlands. Delft is a technical university town. And in Maidenhead, just outside of Heathrow. Those are the two large offices, and then we have sales offices or satellite offices in Paris, Cologne, and near San Diego. We're a provider of expert system technology, but a little bit more specific of real-time expert system technology that allows you to connect to your streaming data sources, real-time data sources, but also to connect to historical data sources. And it enables you to build intelligent solutions quickly on the fly. Eurasian has a group of data scientists that have a specialism in operational intelligence, a subform of predictive analytics, helping you to understand what's happening in your process, how to deal with it, and what to do next. Our experience is quite diverse in different types of industries. At the end of the day, we're always reasoning with real-time data and events. If you look at our engagement landscape, what we do, we have a platform, Use and Oasis EM, which has been sold into the process industry for infrastructure type applications, energy applications, grid applications, commerce, finance, insurance companies, anywhere where there's vast volumes of data and people have uncertainty with respect to decisions that they need to take. The platform is an IDE, integrated development environment, of which we will see parts of it later on in the presentation, that enables you to connect your edges to external systems or your external systems, your workflow systems, collect data from it, streaming data as well, quite important, have deterministic machine learning models reason over your streaming data, and draw conclusions that either go back into your business systems or which are presented directly to an end user. Some of the examples, just some of the examples of where platform has been applied, predominantly because that's our background. It has a good footprint in petrochemical, chemical, oil and gas business. But as we see other companies getting more and more streaming data, we also see our business widening into other industries. Now, along the life of Eurasian, we've seen a few areas where certain of the large companies had white spots in their offerings, for which we created specific apps, package apps, for doing alarm analytics, alarm reporting, and aggregating alarms in real time, and we call that package alarm expert, allowing domain experts to directly apply complex event processing rules on their event and data stream. This we do predominantly in the process industry and in telecom, because those are the industries where the flood of events has led to issues, problems, staffing issues, but also safety problems. But we also see that more and more adjacent industries like infrastructure, road infrastructure, also requires solutions that aggregate the vast amounts of events and alarms, alerts that are being transmitted to central and decentralized control rooms. Our apps we've applied, as I explained, predominantly in process industry and telecom. And here again are some of the our end customers, a lot of blue chip customers that use and apply our technology. Next to our software offerings, we also provide services in the form of our data science capabilities, and services sometimes in the form of our domain knowledge in oil and gas and telecom to specific customers that either want to do big data projects, have already decided or chosen specific technology that they want to do it with, or for customers that are innovating, doing certain key projects in areas where we believe industry will move forward in, like predictive maintenance, for example. Next to that, we have the landscape of hybrid, where our technology, our services, and our apps are used with our knowledge or with our partners' knowledge to develop new solutions for the industry. That's being predominantly done in process industry, infrastructure, and IoT type applications by a wide variety of companies. Again, some examples here like Halliburton, Cactech, and Intech, where this is being done as we speak. In bird's eye overview, Eureson is a company with a lot of background and knowledge in AI, expert system technology, so capable of dealing both with the knowledge and the data analytics sides of problems that you would like to solve, where we go from data science all the way to deploying and rolling out solutions at our customer sites. Now, in part one, we talked about corrective maintenance, preventive maintenance, schedule-based maintenance, condition-based maintenance, and at the end, we talked about predictive maintenance. And just to repeat before going into that a little bit more on predictive maintenance and the capability of our software, predictive maintenance is really maintenance upon indication. It's very different from corrective maintenance, where you repair something when it breaks down, or preventive maintenance, where you repair something without actually having to repair or replace it, because it will not break down up to the next maintenance cycle. Predictive maintenance differs. It uses data, asset condition data, asset usage data, combined with failure modes that are available to determine when it is most likely that specific assets or parts of assets will fail. And predictive maintenance is gaining a lot of interest in industry because it allows companies, if you take a refinery, for example, refinery has a maintenance budget, well, depending on the size, of course, of the refinery and the age of the assets, but between 50 million euros to 200 million euros if we take a refinery that produces between 80,000 and 200,000 barrels a day, or is able to produce that. So those are quite substantial budgets, and the large asset owners are looking at ways to optimize their margins, especially if the oil prices are low. But also, if you look in infrastructure, DSOs, TSOs, so the distribution system owners and the transmission system owners in the electricity networks are looking for ways to be smarter with or smarter about the maintenance costs that they're spending on their assets today. In a nutshell, predictive maintenance does contribute quite well to the bottom line of the company. The refinery example I just gave, at a refinery, maintenance costs contribute anywhere between 10 to 20% of the total budget of the refinery if there's no turnaround. And so if there's a turnaround, it's even more. And if you look at fixed assets such as telecommunication lines, sewage systems, drinking water mains, those companies typically deal with around about 20% of their total costs going into maintenance. So reducing and saving a little bit of maintenance can have a very big impact. And doing it smartly can have a very big impact. Now, the ingredients for doing a predictive maintenance program, we discussed this last session as well. There are some technical ingredients, of course, historical data. Data is the source of everything, you could say. Out of your DCS, out of your SCADA system, or out of other database systems or data warehouses where process data of the asset, usage data of the asset is being stored, in combination with data out of the enterprise and asset management system. So there you have to think about maintenance, databases, applications that facilitate the planning, execution, and bookkeeping of the maintenance process. Maximo is one of them, Maximo Ultimo. There's a number of EAMs packages out there. Luckily, there's not many of them out there anymore, so that you don't have to learn all the different variations out there. In addition to the historical data, you need classification of failures if you want to do predictive maintenance. I'll come back to that later on, but you need to sit down, or mostly companies have already done this, you need to sit down with the asset owners to classify failures, types of failures, and causes of failures, because this will greatly help you develop models that can predict maintenance failures in the future. Of course, you also need analytical tools. If you have the data, you have the classification of the failures and the failure causes, you need analytical tools to analyze, what algorithm or combination of the algorithms together with, for example, a semantic model can best solve the problem that you're dealing with. And for that, we provide a platform, our using platform Use, which is quite capable of dealing with vast volumes of streaming data, allows you to train your model on historical data and then deploy it on the real-time streaming data set. Organization, of course, key very often is that with predictive maintenance applications, you have to start small, you have to involve the asset owners, they have to believe and evangelize the project within the organization. And for that, you need a good champion, good project champion, and good management support. Management support normally is not the issue, because the cost reductions that you can achieve with predictive maintenance programs are quite large and substantial. Now, the last webinar we stopped at this process. I'm not going to discuss it in detail because it's going to be broken down in the next slides. Our typical steps for doing predictive maintenance programs are these. There is a understanding side, because we always believe that issues can be solved by understanding both the domain, the context in which the data is generated, and the knowledge that can be distilled from the data. So we always would like to do a business understanding and a data understanding exercise together with the customer to better understand the context in which the data is being generated, how comes that there are different states detected within the data, etc. Before we start preparing the data, cleaning the data, identifying the features that we require for model training, etc. Before we start with the more hardcore data science side of the process that needs to be undertaken. A typical process for an asset, of course, it depends on the complexity of the asset, the availability of the data, the availability of classification of failures in the data, etc. But a typical process we find that has a duration of 2 to 4 weeks, where we can say for the asset or the larger set of assets of the asset owner, of the operator, it is possible to do a predictive maintenance program based on the data that they have available, based on the knowledge that's available, based on the discipline that they use when entering the inspection data into their EAM systems, their discipline with respect to entering what corrective maintenance has taken place, which is kind of a classification of the failure anytime you enter corrective maintenance activities in your Maximo, for example. And yeah, typically we see that based on the results of a proof of concept, we are able to describe how a wider business adoption of a specific asset-based predictive maintenance program can be rolled out further into that specific company or enterprise. Now, the first steps, and this is this is where I'm starting to break down the process. The first steps in a typical process towards predictive maintenance is to understand, apart from the business understanding, is to understand what the data is that the customer that you provide us with, understand what is being stored, how it is being stored, obviously what engineering unit is being stored in, etc., to understand also the process by which the data is being generated, so that we can prepare, we can cluster the data, we can decide on what additional data is required in order to train models. Very often we find that in order to train models, we need to understand more about the context in which the data was generated, i.e. the process in which the data was generated, and for that we very often request our customers to provide additional data. After that's done, data preparation starts. It really is cleaning and harmonizing the data using bespoke technologies, but at any point in time, of course, being aware that we don't have data leakage, i.e. we don't clean, harmonize the data in such a way that later on in the process we can't properly train models with it anymore. Now, when that's done, one of the first things we typically do in a predictive maintenance project is to determine what features are driving in the data set and are driving towards the detection, possible detection of a failure. And the feature extraction process is one where various algorithms are tested in order to determine what the best mix of different features is that can be used as predictors for a model that is later on trained. Now, here's an example of one of the projects that we did recently, where we received a lot of asset-centric data for a specific family of pumps from different assets, where we received flow, pressure, bearing temperatures, and a whole bunch of other data. And there was a belief, an engineering principle that, speed and the temperature of the bearings in the pumps, or speed of the axle and the temperature of the bearings in the pump, should be correlated over time. And this is true if you look at this little graph here, and the first part of the graph. But at a certain point in time, you see here that the correlation, or the almost correlation between speed and temperature, is broken, and it's broken because the bearing is not functioning appropriately anymore, and at a certain point in time actually leads to damage that causes the pump to be unavailable and causes a lot of havoc in the pump and costs associated to it. So what we, before we get such a picture, what we do with the customer, we typically go through many features, many columns of data that the customer provides, drawings, etc., to understand his process, to understand what's happening. Of course, we have some domain knowledge with respect to rotating and non-rotating equipment being used in process industry, and then to decide based on the data that they provide, based on the symptoms that they describe, how to best select different features from those data sets in order to see which feature can be used to predict a failure from happening. Now, after that's done, so after the feature selection is done, we start model training. And model training is it's not so much as an art; it's a discipline. There are quite a number of different techniques, algorithms out there that allow you to do regression, classification, anomaly detection on data sets, and it is really up to the specific problem, the specific failure prediction that the customer is interested in as to what algorithm or technique, family of technique is most suitable for the problem to solve at hand. What is very important in model training is that you set aside a certain set of your data, and that really depends on the frequency of features available in the data, which is being offered for training and validation. You set aside a certain amount of the data, a certain portion of the data in a kind of quarantine zone which you use later on to validate if the model that has been developed, i.e. the algorithms that have been trained, are capable of predicting failures also on data that the model has not seen yet. And validation is very important, deciding how to cut your data. Do you cut it in half? Do you set aside 70% or 30%? Does your data have very sparse representation of the feature that you're interested in to predict? The way in which you can put data in quarantine is very important, and it's not a technological thing that you need to solve, but you need to use your brains to decide, you know, what the best split of your data is with respect to data, model training and model validation. Now, in machine learning, as I just highlighted, there are a number of types. You could call them families of different types of machine learning, and quite a large number of algorithms nowadays that allow you to train machine learning models. The result of training is a model on the data that you provided with. And the types of machine learning really can be subdivided into 4 different ones. You have supervised learning, compared to learning or being trained by a teacher. The teacher tells you how to react or what to do or how to calculate a specific value. And supervised learning the analogy is similar. With the data come the classification of the failure or the value of the temperature that you want to predict, or the anomaly that you want to prevent, i.e. there is a classification or the value that you are or want to predict is part of the data set, is indicated in the data set. And supervised learning is the technique that you mostly apply in predictive maintenance programs. Now, another technique is unsupervised. Unsupervised learning does not allow you, typically does not allow you to predict with great precision, to predict a value or to predict a certain symptom that's occurring. Unsupervised learning is, you could say, training without a teacher. You're not being told what the end result is, and unsupervised learning algorithms typically only tell you that there is a deviation from normal, i.e. it is not something that the algorithm has seen before. And unsupervised learning is very applicable also in predictive maintenance cases where the customer, for example, does not have a large amount of historical data available, or is not capable or has not done any of the classification efforts to pinpoint the failure and the cause of the failure. Now, the other types of machine learning, semi-supervised learning and reinforcement learning, are really techniques that are not very often applied in the maintenance domain because they require a little bit more work, especially reinforcement learning with state model and action models. It's more something that you would use or apply to verify if maintenance personnel is carrying out a specific task in an order that you expect them to carry it out in. As I said, there are many different types of machine learning algorithms. So linear regression, most of you probably know linear regression from university and school. It's very fast, of course, very easy to understand. It is also very prone to overfitting. Very prone to overfitting. There are disadvantages. It's not suited for nonlinear complex relationships. It is very appropriate to have a first look at the data set with linear regression models. Decision trees, fast again, quite reduced to noise, i.e. if the data that you're dealing with is very noisy, accurate, but they're not very appropriate for the domain that we're dealing with, i.e. The maintenance domain. They're more appropriate for doing medical diagnosis, credit risk analysis based on the customer that signs himself in on a credit card request form, etc. Neural networks, a technology that's been around for decades. Really now we have computing power and the resources to apply neural networks in a very cost-effective manner. They're very powerful. Linear, nonlinear relationships can be trained with them, and you'll see that later on in the presentation as well. And it's very appropriate to deal with image, video, but also to apply them in the process as what we sometimes call soft sensors in areas where you would like to calculate a value that does not come from the process. And we'll see later on that they're quite well suited for that. And so on. I mean, support vector machines is another one that's, since early 2000s has gained a lot of interest in academia, but also at different companies. Very robust to noise, very capable of dealing with uncertainty, capable of dealing with nonlinear and linear processes. There's various forms of it. Support vector machines are typically used to classify or determine what type of symptom is currently active. Support vector regression, obviously, to determine what the value is of a specific process point that is not measured. And then, of course, k-nearest neighbors, simple, powerful, easy to use. It's really not machine learning. Had a discussion about that actually this morning. Because there's no real training involved, it's more determining if the signal that you're processing is comparable to a signal that you've seen before, which is more descriptive and less machine learning. Can be used quite well on data sets that have a very low dimension, i.e. data sets that are not very variable in their make, so to say. But yeah, k-nearest neighbors is a technique that can be applied also within the maintenance domain if you're looking for specific patterns of data that reoccur on your assets, on your bearings, on vibration sensors. Then KNN is a technique that can be used to pre-qualify that a machine is entering into a certain state, or an asset is entering into a certain state where failure later on may be happening. Now, in the example here, we trained, this was an example we did a few months ago with one of our customers. We saw the picture earlier on where we saw somewhat of a correlation between the speed of the pump and the bearing temperature, and they were, between quotes, in sync up to a certain point. At that certain point, bearing temperature started gradually, slowly increasing, but that slow increase at a later point in time actually leads to a failure of the pump. Now, to address this specific example, like always at with our customers, we look at your data, we look at the context in which the data is generated, we look at how well the issues have been classified, and then we select out of quite a large toolbox inside use what algorithm is the most appropriate for the problem that we're dealing with. And in this case, it looked to us as, a neural network could quite easily deal with the problem. It will be quick to train, quick to deploy, very cost effective. Neural network can also be retrained based on new data coming in if you know the state, the context in which the data is generated. And we apply the neural network here with some of the details, the number of hidden nodes, etc., but it probably goes too far on a training data subset of our pump data. When the model was trained, it was validated. There was a slide later on that. And obviously, what our customers are, once I've trained the model, in Python or in Julia or in other languages, how do I actually deploy it? Well, the deployment of the model, if you've trained it inside our environment, the use environment, or other environments, can easily be done, can be done within the use environment. It's capable of doing feature detection, capable of doing state detection, and deploying the model in real time and keeping track of accuracy of the model such that it can be updated and tuned over time. Now, the results of the earlier example that I gave were quite surprising because we achieved quite a high number of positive detections on the different data sets, on the data that was set aside in the validation step. And it shows, we have here in this little slide The neural net set out against what people would normally do, look at the correlation between the temperature of the bearing and the speed of the pump. And as you can see, both graphs almost have the same time basis. If you apply, simple correlation, you get a lot of false negatives and false positives where the bearing temperature is not closely correlated to the speed anymore of the pump, but there is no need yet to alarm or alert someone within the maintenance department. So here with traditional methods in this area, you get a lot of false negatives and false positives that are an indication of failure when actually nothing is wrong, everything is running as normal. And with the neural net, you get a very clear event notification that can be put back into your Maximo systems or other maintenance systems to indicate that a specific overhaul of the bearing in case has to be done on a specific asset prior to it failing. Of course, what's important here is the PF curve for all people in the maintenance domain. The PF, the potential to fail, and the actual failure. You have to have enough lead time to allow, between quotes, the logistics to take place from scheduling the maintenance action, planning it, having the right people, and of course spare parts if required to go to the asset and do the actual replacement. Okay, summarizing, Eurasian, very strong partner, a good partner in developing predictive maintenance programs with asset owners, with you. We have a lot of experience in big data IoT, it's immensely popular right now. And our background is in AI and predictive analytics. We're active in process industry, telecom, smart grid, smart cities, and infrastructure, of course, with more and more predictive maintenance programs being set up for infrastructure companies that own large gas networks, large oil pipe networks, infrastructure such as fiber, copper cable, and in maritime we've seen quite a huge jump, also because maritime systems are providing more and more data back to shore. A huge jump in predictive maintenance programs and keeping the uptime of large ships as high as possible. We have proven track records with quite a number of diverse customers in Northern Europe, Northern America, and the Middle East, and some in Asia, left and right. If you're interested to engage with us, drop us a note, send us your email details and the questions that you're dealing with in the area of predictive maintenance. Okay, now let's open up to the questions. So I'm looking at the Q&A panel here. So one of the questions here, on my view, is with respect to let me read out. So what type of algorithms are most predominantly used for predictive maintenance programs? Now, the type of algorithms are very often driven by the specific problem, the specific case, the availability of data, of course, that the asset owner has and the problem that he's dealing with. And so there is no one, let's say, answer to this. The right answer is that we're either dealing with a classification of an issue, meaning that you are interested to determine if a certain issue is occurring, overheating, heating, vibrations, for example, if you're not are able to measure that, or the determination of a specific value or expected value, the soft sensor approach that I mentioned earlier on. And yeah, there is no one straight answer. SVR, ANM, SVM are very commonly used, but if there is little to no classification, but there are specific reoccurring patterns that you would like to identify, combination of KNN with other pattern matching algorithms could be used, could be employed to as a prelude to a predictive maintenance program that uses real machine learning models. Okay, here's another question. How much data is required for predictive maintenance on a turbine? Now, the amount of data, it's not so much the amount of data. It's not a, let's say, a quality indicator or a go-ahead indicator for doing predictive maintenance. The right data needs to be available. We have been in situations where there's been little to no correlation between the data that we received and the features that, you know, the specific features that the customer wanted to predict. And quite early on in the process, and that's why we do this proof of concept, proof of value part at the beginning, quite early on in the process, it will become clear to the customer that, you know, he either needs to start logging more or investigate if, you know, other data sources are available within his enterprise, within this company. But the quantity of data is not a measure for the success. We do need enough. If you think of machine learning, if you're not taking a deterministic approach, you're trying to indicate, find causes of failures and early indications. We do need some volume of failures. So things have to go wrong in the past if you want to apply the machine learning methods that we just discussed, if you want to apply neural nets on your streaming data. So quantity of data is not so much a key as to success. It's the availability of the right data in combination with availability of a large enough, and that really depends on the domain, a large enough number of occurrences where things went wrong and in which you're interested in preventing that. And think of this, each time that within your Maximo system you enter a ticket, or your maintenance engineers enter a ticket for corrective maintenance, I mean, if it's corrective maintenance and it was unplanned, i.e. it doesn't appear in the to-do list in the Maximo ticket for that specific asset, it means that something broke down. If they're preventatively replacing it and it wasn't on the ticket list, it means that something is expected to break down. So that's already kind of a pre-classification of failures as such, i.e. you don't have to run everything to failure in order to start machine learning projects. Okay, looking at the time and looking at the questions, there are a few more questions. I encourage you to get in contact with us on the last slide here. That's the Q&A slide. Our contact details, and of course you have our details via the invite by which you joined this meeting. I encourage you to put other questions on the email. I have to keep an eye on the time. We've run it slightly over the allocated time. I hope that you enjoyed the webinar, and I surely hope to see you back on part 3 of the predictive maintenance webinar. Thank you very much.